This is our ninth topic for the course ENSC107. In this topic, we will discuss the viscous flows of fluids in a duct or pipe or any closed conduit systems. Now, first, let's define or let's describe what is an internal flow. So, fluid flows can be classified or can be categorized into these three applications. The first one is the internal flows, also referred to as or also known as pipe flows, although later we will discuss the precise description of this because it's not about the geometry of the conduit. Okay, so the first one is internal flows. The second one is the open channels. Then the third one is the external flows. Okay, so when we say internal flows, that means that the flow is inside a solid boundary. Okay, so for example, this is our conduit or solid boundary, then the flow is inside. Okay, so that's inside. However, a more precise description is that even if it's inside, it must be fully filled. Okay, so it must be fully filled such that no free surface exists. And when we say free surface, that means that there is an exposure to the atmospheric pressure. Okay, so again, internal flows are fluid flows. Where the fluid flows inside the solid boundary, and it must be fully filled, okay, such that no free surface exists. Now, the geometry could be a circle, or let's say a square or a rectangle. For example, in the duct systems, ventilation ducts, or air conditioning systems. So the typical ones would be the rectangular and then the circular. Now for the open channels, we have this flow. It's typically described as the flow in a canal. So for example, this is our solid boundaries and this is our fluid. So it's still inside. It's still inside the, or it is still contained in the solid boundary, except that there's an existence of the free surface. Okay, so this is our free surface, and again, when we say free surface, then that means there is an exposure to the atmospheric pressure. Okay, so that's the difference between the open channel and the internal flow, and therefore a pipe is, a circular conduit, but if it's not fully filled, then therefore there's going to be an exposure to the atmospheric pressure, and therefore in this case this will be under the open channel applications. And for the external flows, if we have this airfoil, for example, is especially shaped solid boundaries, but the flow is outside, or it is over the solid boundaries. Okay, so again, for fluid flows, the application, we have the internal flows, we have the open channels, and we have the external flows. So for now, in this discussion or in this topic, we'll just focus our discussions in these internal flows applications. By the way, where do we find this internal flows application? We can find this in the, for example, water supply systems in the building, ventilation systems, and even in agriculture we have the drip and sprinkler, right? Sprinkler irrigations systems, irrigations systems. Okay, so now let's get into the detail. Pipe system basically includes, for example, we have a reservoir over here, and then we have to transport the water into this reservoir. Therefore, we will need a pump, right? And this pump, of course, we will also need pipings, or the pipe itself, plus the fittings. Example, we have an elbow, and here let's say we have a T, so another fittings, and here let's say we have a valve, right? And then another pipe, for example, and here let's say we have a 45 degree elbow, then here again another 45 degree, then it's connected to this reservoir. So this is just an example. That's right, this pump, and then we have elbows, T's, and valves. They are called as fittings, valves and fittings. Okay, so in order to transport this water or this fluid from this point, say this is our point 1 to point 2, then of course we need to exert energy, right? And that's why we need the mechanical device called the pump to increase the pressure. However, as the fluid or as the water is being transported, it has a lot of frictions along the pipelines. Okay, so we have head loss, say friction, okay, which just simply the head loss. And that's why we need to compute the head loss. We need the value of the head loss so that we can properly size the pump. And also if we want, for example, a proper flow rate or things like that, then of course we have to take into account the head loss. And even in a straight, let's say a single pipe, and let's say it has a fairly long length, then of course, even though even though it does not include any fittings or valves, but due to the fact that it is long, then of course, let's say this is our point 1, then this is our point 2. If we measure the pressure at point 1, and then we measure the pressure at point 2, we would see that the pressure of 2 would be less than the pressure 1. Why? There's gonna be a pressure loss, and which is related to the frictions. So sometimes we just neglect the head loss. Remember when we used the Bernoulli's equation, we didn't take into account the presence of the head loss, and they're actually applicable to some degree. But in our previous lectures, we also discussed the conservation of energy, wherein wherein even though we have this Bernoulli's equation, so z1 plus what else, the velocity head. Okay, so plus some energy terms, like for example, if we have a pump, then we add a term here, energy added, then the pressure again at 2, velocity, the elevation head at 2, plus if there are, for example, turbines or other fluid motors or mechanical devices that removes energy, then we just include another term, that's HR, plus the head loss. All right, so these are energy inputs, energy that that's transferred into the system, and this one is be the energy that goes out from the system, right? And this head loss, this is actually what we're talking about, and this is actually later on we will focus much on this head loss. How do we find this head loss? What is the equation of this head loss? If we have the diameter, the length, and then the velocity of the fluid inside the pipe, then what's going to be our equation for this? Okay, now we'll talk about the Reynolds number. Okay, the Reynolds number. Okay, so the Reynolds number, it's actually one of the dimensionless numbers that you'll encounter in the study of fluid mechanics and even heat transfer. Okay, so when I say dimensionless numbers, they have no units, but they describe some situations or some principles regarding the, let's say, the fluid flow. Okay, so the Reynolds number, it's named after Osborne Reynolds. Okay, Osborne Reynolds. That's in 1842 to 1912. Okay, so what he did is he set up an experiment, and for example, there's a tank of water, and then inside that tank of water there is a something like a tube, a glass tube with a bell mouth. Okay, and then it exits here. Let's say we have a tube that's going downward or something. The main point is there's a large tank filled with water, and then there's a small tank. Okay, so this is small tank. There is a tube that goes into the center line, that goes to the center line of this glass tube. So if we draw this inside view, we have this large tank, and here we have a glass tube, and here we have the small tank, and then another tube right here. Okay, and this small tank is actually filled with dye. Okay, and then this one is filled with water. And he investigated that with this particular velocity, then what would be the flow of the dye. So if we draw it right here, then another one. So he noticed that for lower velocities, he noticed that the dye has a smooth flow profile. Okay, so something like this. But then if he increase the velocity, then he noticed that there's actually a formation of eddies, and therefore the profile is no longer smooth. Okay, so this will be the dye profile. And for this smooth flow, this is referred to as the laminar flow. Laminar in laminates, right? Laminar, where a very smooth flow, so that's laminar flow. And this one, he termed it as the turbulent flow. Okay, so how is this, or why is this important to determine the laminar flow or the flow is turbulent? It's because these are related to the pressure drop. Okay, so if you notice that if you have a turbulent flow, then of course you have a lot of eddies, you have a lot of frictions right here, and therefore you have an increase in the pressure drop. But if your flow is laminar, then of course you have a less friction. So therefore, the Reynolds number or the symbol is RE. The Reynolds number is used to predict the type of flow, whether it is laminar or turbulent. Okay, so how do we know the Reynolds number, or what is the mathematical expression of the Reynolds number? It is given as RE is equal to V rho times LC all over the mu. Okay, so this one is the velocity, and this one is the fluid density. This one is the characteristic length, and this one is the viscosity of the fluid. So it's a dimensionless number. This again is the velocity, this is the fluid density, this is the viscosity. Now this one, the characteristic length, so that depends upon the geometry. Okay, so it's not the length, it's actually the length that characterize the flow. Okay, so the equation for this is actually 4A all over P sub W. Okay, where P sub W is referred to as the wetted perimeter. This one is the cross-sectional area. Okay, so wetted perimeter is the portion of the wall surface, or the portion of the perimeter that's actually submerged in the fluid. Okay, so for example, if we have this, we have a circular pipe. Now we have a fully filled flow. Then of course our LC would be 4A. So what is the cross-sectional area? We have pi d squared all over 4. And what is the wetted perimeter? That's actually the entire circumference. So that's just pi d. And to simplify, since we have 4, we have also pi, and we have d squared in the numerator. So this one cancels out. Therefore, for circular pipes, internal flows, the characteristic length is equal to the diameter itself, right? But for, let's say we have a square or a rectangle, then of course you have to compute the wetted. You have to compute the characteristic length. Okay, so how do we know if the flow is laminar or turbulent? Okay, so there are a lot of numbers. If RE is less than 2,300, then the flow is said to be laminar flow. And if RE is greater than 4,000, then the flow is said to be turbulent flow. And in between, if we have this 2300 and our RA is in between the values, then we have a flow that's called a transition. Okay, so this is what we call as the critical Reynolds number. Critical RE, and this is only true for internal flows. If we're dealing with open channels, then we have another set of critical RE values. Okay, so by the way, you would also observe that for different textbooks you have values like, for example, 2000, and then for other textbooks they use 2300. Okay, so don't stress yourself with this because they're just near each other. All right, now we'll talk about the development of flow. Development of flow. I have included this topic in our lecture handouts because you'll encounter this in your course heat transfer later on. Although for now we'll just run through it, but we'll not go much into the computation of this. Computations regarding this topic. Okay, so for example, we have this section of the pipe. And let's say this is our center line. Okay, and imagine there's a stream of fluid that's about to enter the pipe. Okay, so there's a stream of fluid having a uniform velocity. Okay, when I say uniform velocity, that's the velocity is the same in all the y direction. Okay, so along the y direction it has the same velocity. Okay, so imagine that this fluid is actually moving and it's about to enter this pipe. So the moment it touches this solid surface, then of course, because of the presence of the viscosity, because the presence of the shear stress, then of course the fluid layer that's adjacent to the wall surface would actually retards. Okay, so instead of having this velocity, this length of velocity, you have a slower velocity. Actually, the assumption is that they call it as the no slip condition. Okay, so that means that the fluid that's attached to this or next to this adjacent layer, theoretically it stops. Okay, so the next layer would have this velocity profile, and then the next layer would have an increased velocity profile or something like that. Okay, until we have a form something like this. Okay. Okay, so that's our velocity profile at this entrance section. Okay, now if we check another profile right here, what we'll see is we'll have something like this, straight, then curves again. Okay, this will be our velocity profile right here. Now if we have some, at some length, we will develop a profile that's actually looks like this. It's a smooth parabolic profile. Okay, so you'll notice that because of the presence of the wall surface, then there's actually a retarding of the velocity. Okay, so here at this point, from this point to this point, we have actually a variation in the velocity as compared to this fluids before the before entering the pipe. Okay, so and then right here we'll have this variations, but right here, this region right here, they have actually the same velocity as the ones in this free stream. Right, so here we have the same velocity, but right here we'll have actually the same velocity. Okay, so this one, they have the same velocity as this. Okay, so you would notice that it's actually creating a layer, right? So it's actually having like this. Okay, so this is what we call as the boundary layer. Okay, so recall that the boundary concept, the boundary layer concept is that it says that the viscous effects is only significant within the boundary layer region. Okay, so that means that this region, this region will be the where the viscous effects are important or significant. And this is actually, if we draw this in three-dimensional view, what we get is something like a funnel shape. Okay, since this is a perfect circle, then of course it's going to be a funnel shape. And the distance from this to where it gets a smooth velocity profile, that's what we call as the entrance region. Okay, so if we have a smooth velocity profile, that means that our flow is a laminar flow. And for a turbulent flow, we'll have something like this, turbulent flow. Okay, so it is flatter as compared to this. Now, if we graph the shear stress and then the pressure drop, we'll see that our shear stress is something like this. Okay, so at the entrance region, we'll have a higher shear stress, but when you get to this fully developed flow, then you'll have a constant shear stress. Okay, so for the pressure drop, it's also almost the same. So at first you'll have a higher pressure drop. That's because we have a turbulent flow in this section. All right, now that's all we have for this development of flow. As I've said, this is just an introduction because you'll encounter this in your heat transfer course, especially when dealing with convection heat transfer. Okay, so we'll continue our discussion in the next video.